These are few important derivations from ray optics, the optical instruments part. Normally, microscopes and telescopes are discussed in this category. The first case under microscope, the simple microscope. So it can be even a single convex lens used for seeing the objects magnified. So that's why it's called a magnifying glass. For higher magnification or magnifying power, the focal length has to be of short, or the power, which is 1/f, has to be very large for the lens for better magnification or magnifying power or angular magnification. So a single convex lens of short focal length can act as a simple microscope with good angular magnification. There are two cases normally for the image formation. One is the maximum magnification or angular magnification case, when the final image is formed at the near point. Your ray diagram, convex lens, principal axis, optical center, focal length. Object is placed within the focus. One light ray parallel to the principal axis will pass to the focus. The second light ray passing through the optic center from the top of the object. The extended light rays will meet. The refracted light rays are diverging away, so the image form will be virtual. To get the final image, the light rays have to be extended so that they meet and form the image. IM stands for the image. Light rays forming virtual image, the extended part and the virtual image must be represented in dotted lines. Arrow mark is a must for all the ray diagrams. If there is no arrow mark, the board rule is no mark strike. The image is formed at near point. So wherever we get the image after the ray diagram, the distance from C to I is marked as the image distance, which is equal to the near point distance. It is normally represented as T. Negative sign because by sign convention, the light rays are going from left to right, but the CI is measured opposed to the incident light rays, minus T. C2O will be the U. Now, the values CO is object distance U, CI is image distance, which is equal to the near point distance with negative sign convention, and C2F is the focal length. Now, if you mark the theta I and theta O for finding the angular magnification, theta I is the angle subtended by the image at the near point, is already at the near point. Image formed at near point, what angle it makes at the lens. Actually, lens, where we keep the eye, the observer's eye will be close to the lens. So lens will be taken as the point where you subtend the angle. The angle subtended at the center of the lens, which is taken as I, by the image formed at near point. So if the image is formed at near point, draw two lines from the top and bottom of the image to the optic center. That will be the theta I value. For finding theta O, the real object should be transferred to the near point. To avoid confusion in the diagram, we just recreating another situation. This is a point C and this is the point I, which is a near point. The object will be transferred from this position to the near point. The angle subtended by the object placed at the near point. The angle should be taken again at the optic center of the lens or at the eye of the observer. So that angle is theta O. So theta O, when you find the object has to be at the near point, get the two light rays or lines from top and bottom of the object to the optic center, that will be theta O. For the image, as per the case, here image is formed at near point. So from top and bottom of the image formed at near point, we draw the lines to the optic center. That angle will be theta I. For image, it depends upon the location of the image. We have two cases, image formed at near point and far point. But for object, it is always, for a microscope, the object has to be always at the near point, because that's the only case real object can be kept close to the human eye without any lens. If you bring closer than this, the image will not be formed clearly on the retina. This is the closest distance which gives maximum magnifying power for the eye without any optical instruments. So when you compare the image formation of the lens, you should compare the maximum power of the eye. That is why every case theta O for a microscope is measured with the object at the near point. Image, it depends upon the case. Whether image is formed at near point, with that you find the angle. If it's formed at far point, with that image you find the angle. Now the magnifying power is defined as the ratio of theta I to theta O. Theta I is the angle subtended at the eye by the image formed at far point or near point. Theta O is the angle subtended at the eye by the object. For a microscope, it must be at the near point and seen without any optical instruments. So this can be approximately tan theta I by tan theta O. Now finding diagram tan theta I and tan theta O. So tan theta I will be using this triangle OBC. Tan theta I will be OB by OC, and tan theta O will be IB dash by CI. Substituting, IB dash is actually same as OB. We just transferred and given a different point for B dash. So OB same as IB dash. It's just the object transferred to another location. So that IB dash and OB get cancelled from that. It becomes CI by CU. CI is V. We'll give the minus T later, and CO is U. So it comes as V by U. So angular magnification or magnifying power, we got same as the linear magnification, which is V by U for a convex lens. For transferring this into constant terms, we already have lens formula 1 by F equal to 1 by V minus 1 by U. If you multiply throughout by V, V by F equal to 1, V by P is 1 minus V by U. Get V by U from this, we'll go left and V by F come to the right. So V by U is magnifying power M. Now you can give the value of Vs minus D. So it will come as V by U M 1 minus D by F. It comes finally 1 plus D by F. That's a final formula for magnifying power of a simple microscope when the image is formed at near point. It's very clear from this. Short focal length lens can help in improving the magnifying power.